Okay, so in part A, they want us to calculate acceleration. Acceleration is final velocity minus initial velocity divided by time. Because this is a velocity versus time graph, I can read all of that data directly off the graph. All right, so it's between 7 and 9 seconds, so my final velocity is here at time 9 seconds, and it's what value? 0. Okay. And 7 seconds will be my initial, and my velocity at time 7 seconds is 3. Okay, obviously between 7 and 9 seconds, there are 2 seconds. Okay, so 3 over 2, right, but it's going to be negative, because 0 minus 3 is negative 3, is going to be negative 1.5 meters per second squared. Okay, all right, how many people have done B? Okay, I'll give you guys a couple more minutes, and we'll look at B. Okay, so if I'm looking at part B, those would be the lines I would need to use, okay, if I want to get my shapes, okay? Because remember that getting those shapes means that I'm taking the average velocity during that time and multiplying it by the time, which calculates displacement. During this first part here, during the first second, it's accelerating. It's going from 0 to 1, so its average velocity is 0.5, half the height of the triangle. Okay, so 0.5 times 1, okay, is 0.5. So this is going to be 0.5 meters. Right? Then I've got this big rectangle. So I'm only going to 7 seconds here, right, for the displacement, so between 0 and 7. So this rectangle here, okay, will take care of part of that area. It would be assuming the object is traveling at 1 meter per second for the next 6 seconds, which means 1 times 6 is 6. Right? So we go 6 meters during that time. All right, during this part of the graph here, the object is accelerating. It's going to go from 1 to 3, okay, so it has a height of 2, okay, so the height divided by 2, so 2 divided by 2 is 1, okay, and the base is 2 seconds, okay, so we'll be looking at 2 meters for that one. And then we have this rectangle here, and it has a base of 1, 2, 3, and a height of 2, so it would also be 6 meters. So we should have 14.5 positive meters for our displacement there.
We have different shapes, but the same answers.
Then you're good, because there's more than one way to draw those shapes. We could have drawn a rectangle that went all the way down instead of all the way across. As long as all the area is accounted for, it doesn't matter what shapes you pick. Yeah. All right, how many people have done C? Okay, so I have to get one more area to do C, right? I've got, because it's for the whole trip, so I got that last triangle there to do. I'll give you guys a couple minutes to get ahead of me again, okay? And then we'll look at C. All right, so if we're gonna get average speed, okay, we need total distance and total time. We've already calculated most of the displacements, which we can use for distances as long as we make them all positive, which they are, because it's only moving forward here anyway, okay? Then we can just divide by the total time. So we just need this last triangle that has a base of 2 and a height of 3, so 3 times 2 is 6, divided by 2 is 3 meters, okay? So now we have 17.5 meters as our total distance traveled, okay? And then we just divide that by the total time, which is 9 seconds. Okay, and if we go 17.5 over 9, we should get 1.94 meters per second. Okay. Everybody all right with that? Okay, and then the last one wants us to calculate an acceleration between 2 and 4 seconds. So that means we're back to this formula here, okay, where we have where we have A equals VF minus VI over T, right? And so when we're looking at this here, we have VF at 4 seconds being 3, VI at 2 seconds being 1, and that takes 2 seconds. So 2 over 2, 1 meter per second squared, and it's positive because it is going faster and forward. Okay. All right. So here's kind of the trick with the graphs. The graphs and the formulas on your formula sheet go together. You're gonna use the formulas on your formula sheet with graphs, okay? Unless the graph is a single line, then you just use y equals mx plus b. Okay, but for other graphs, ones like this that have lots of different types of motion on them, you're gonna use the formulas on your formula sheet, okay? And those formulas are this one, okay, that calculates average velocity, which can be expanded to this. Okay, so velocity equals, average velocity equals total displacement divided by total time. That's final position minus initial position over time. Okay, this formula here, especially this version of it, okay, that version of that formula, would I ever use with a velocity versus time graph? Does a velocity versus time graph give me position? Then I would never use that version of the formula with a velocity versus time graph. Okay, and that's not something I want you to memorize. That's something I want you to be able to look at a graph and go, well, I can't use that one. This graph doesn't give me that data. Okay, it's just like reading a word problem. When I read a word problem, I write down all the things it gives me, and then I go, oh, I don't have time. Well, I better find a way to get that. Okay, you're doing the same thing with a graph. Okay, would I use this version of the formula with a velocity time graph? We did. Right? When we calculated average speed and when we calculated total displacement. We used it for both of those, right? I manipulated it for D because I can always get the velocities off of this graph. I can always get the times off of this graph. Okay, so that is a formula I could use with a velocity time graph. Okay, similar with this one, okay, the scalar version. I could use that with a velocity versus time graph. I could use it with a position versus time graph. I can get all of that information from both. Okay? Okay. Is there a type of graph I can't use that formula with? Okay. It gives me acceleration, provided I can find initial and final velocity and time. Which graph can I not use that formula with? I can't use it with a position versus time graph. Okay, a position versus time graph will not tell me the initial and final velocities. I can't get that from that graph. Okay, so that formula won't work with that. That's what we gotta be able to do is, okay, I've got this graph. What can I read off of this graph? That we kinda have to memorize. Okay, what can I get off of this graph? And what formulas can I use with it now that I have that stuff? Okay, that's the tricky part. The math isn't tough. Multiplying, dividing, adding, and subtracting, like there's nothing difficult about the math. It's figuring out what math to do. That's the trick with physics. Okay, especially this stuff. What math do I do? Oh, well, I do this math. Okay, that's why I can teach physics. Okay, I'm not terribly good at math. Okay, like I was beating my head against the table the other day trying to help my son with his math 10. I'm like, oh my God, I can't do this stuff. This is over my head. And I teach physics. Because physics involves this kind of math. It's easy. Okay? I don't have to be good at math to be good at physics. In fact, some of my best physics students were not terribly good at math. But they can see it. Okay? Physics is about seeing what's going on and knowing what to do, not necessarily how. Okay? You can always figure out how, okay? But you can't figure out what. Okay? All right, so I'm saying that because I want you guys to take some solace in this, because I know there's this like almost societal feeling that math is hard and I'm not good at math. And while I don't buy that, okay, anybody can be good at math if they put their mind to it, okay, you don't have to be good at math to do physics. Okay? In fact, some of the people that struggled the most with physics were the ones who were really good at math. Because they're just like, can I just do the math? I'm like, no, you have to figure out which math to do. Can't you just tell me that? No, that's physics. Figuring out what math to do is physics. Okay? And they struggle with it because they were really good at math. I could throw them a really complex thing and they could do it. Okay? But could they figure out what to do when I just gave them a problem? Not always. right? So take some solace in that. You don't have to be great at math to do physics. Okay? It doesn't hurt, okay? Make no mistake, it doesn't hurt, okay? But it's also not necessary. Okay? All right, I would like you guys to try, actually, in your digital workbook. So you'll need the digital workbook open because you're gonna use this same graph for like 6 or 7 questions. Okay, now, what kind of graph is this? It's a position versus time graph, so we're switching back, and that's what we have to be able to do, is we gotta be able to switch gears on the fly, okay? So position versus time, the velocity versus time, what we do is different, what we read is different, okay? So, this is on the bottom of page 7, okay? This graph is on the bottom of page 7 of your digital workbook, and then there's some problems that go along with it on the next page, okay? They start out really easy. Like question number 1, what's the position at 0 seconds? That's just reading the graph. Okay, like those are really, really easy. Okay, and then total displacement. Okay, figure out how to do that. I'm gonna give you guys a bit of time, and then we'll walk through each of these. Okay, together. Okay, so number 1 is basically just reading the graph. Okay, what's the position at 0 seconds? Well, it's a position versus time graph, so I can read that directly off the graph. The position at time 0 seconds is 30 meters. At time 6 seconds, I'd say negative 15 probably. Okay, and at 14 seconds, right in between 2 grid lines again, I'd say positive 25 meters. All right, so those are just read them directly off the graph. Okay, give you guys a few minutes to get that one done there. Okay, so on number 2, they want us to find the total displacement. If I go back to my formula sheet, okay, total displacement can be calculated using this formula, okay, or this formula. Which one's my best bet for this graph? The first one, because it shows position and time, okay? That one might work, but I don't really have enough information to use it. Okay, so final position minus initial position. So the total displacement to 2 seconds. So my initial position is going to be positive 30, and my final position is going to be positive 50. All right, so if I'm putting that in, okay, positive 50 minus positive 30 is positive 20 meters as my total displacement to 2 seconds. Okay, total displacement to 4 seconds. Well, my initial position stays 30. Okay, but my final position is now positive 4. Okay, so I would have positive 4 minus 30, which would give me negative 26 meters for my displacement. Is the negative important? It is. We're going backwards, and just displacement's a vector quantity. Oh, and Cam just left. Okay. Next one here is to 11 seconds. Okay, so again, our initial position is still going to be 30, but at time 11 seconds, that's right here, okay, our position is 0. So 0 minus 30, that'll be negative 30 meters to that. Okay, questions on that? Okay, keep going then. Okay, so the next one wants the total distance for the same times. So that was 2.0 seconds. What was it? 2, 4, no, 2, sorry. That's the wrong one. 2, 4, and 11, right? Okay. So, calculating displacement, we only have to go final position minus initial position because it's always wanting the shortest route between the first and final points. But because distance is scalar, I have to calculate how far I go in each section of the graph because I have to add them all up. Okay, so for 2 seconds it's easy because it's still just the same section of the graph. It's still 20 meters from 30 to 50. Just I don't put a positive on it this time because it's scalar, right? But where it changes is when I go to 4 seconds, because now I change direction. That makes my displacement get smaller, but my distance always gets bigger, right? Because it just cares about how far I go. So I'm going to have this initial 20 meters here, but now I'm going to have this additional, no, sorry, not 26, but 46 meters, because I'm going to go from 50 down to 4. Okay, everybody follow what I did there? Okay, so I still did final position minus initial position. I still did 4 minus 50, okay, but I got 46. But I just made it positive because, again, I'm dealing with a scalar quantity. So now the total distance traveled to 4 seconds is 66 meters. Right? And then to go to 11 seconds, I got to keep going. Okay, so I'm going from 4 down to negative 42, it looks like. Okay, so that's going to be another 46 meters. Right? And then, well, but without the negative. And then up to 14. Okay, so I'm going to go up to here, and then I'm going to change direction again. So from negative 42 to 27. Okay. All right, so that's 69 meters there. Okay, and then I've got to go to 14. Which is down another 2 meters, it looks like. So add on another 2 meters for that. So 71. $183 meters. Okay. Now, is that a little bit more work, that one? It is, but it's always the same thing. Right, so just look for those changes in the pattern, okay, changes in the line, and each one of those changes requires you to start and stop in your step. Okay, so that's for distance because it's scalar. Okay, for displacement, it's a lot easier. It's just final position minus initial position. Okay, and this one wants more displacements. Okay, so let's do those ones and then we'll move on to something else. So, okay, try those displacements there, and we'll have a look at those. Okay, let's look at these ones here. So, if I want to find displacement for these here, again, we're looking at this formula because it's what we can get off of the graph. Okay, final position minus initial position. So between 2 and 4 seconds, okay, well, my displacement or my position at time 2 seconds is 50. Here it's 4, so that's negative 46 meters, which we had already calculated in the previous question. All right, between 4 and 8 seconds. All right, so here's where we are at 8 seconds. Okay, that looks like 33 to me. Okay, so we're starting at, or our final position is negative 33 minus 4 is negative 37 meters for that one. And then between 12 and 16 seconds, so my position at 12 seconds is positive 20, and at 16, it is positive 12, negative 8 meters for that section. Okay, everybody all right with that? The trickiest part of that is actually getting the right numbers off the graph, right? Otherwise, it's just subtraction, which is easy. Okay, I would like you guys to do question number 6. Okay, it's asking you to do some velocity calculations. So, I've got a position versus time graph where I can read position and time directly off the graph, but they're asking me to calculate velocity, which means I should probably use this version of V equals d over t. Okay, so final position minus initial position divided by time, right? So for between 0 and 2 seconds, okay, we'll have 50 minus 30 over 2. Initial position was 30, final position was 50, okay, which is going to give us 20 over 2 for positive 10 meters per second. Is the positive important? It is. Okay, between 2 and 4 seconds. Well, we've already calculated the displacement for that a few minutes ago. Okay, so it would be the final position was 4, the initial position is 50, and that takes again 2 seconds. All right, so 4 minus 50 is 46. 46 over 2 is negative 23 meters per second. Okay. And then the next one is 4 and 7 seconds. So at time 4 seconds, okay, our initial position is 4, and at 7 seconds, that's right there, it would be negative 24. Okay, and that's divided by 3 seconds. So we got 20 over 3. Sorry, no, 28 over 3. Okay, negative 28 over 3, and that's going to be 9 point something. Okay, did I misread the graph?
It's 9.3.
9.3? Okay, negative 9.3 meters per second. Okay, is that all making sense? All right, so we'll have a bit more time to play around with graphs next week. And we'll have our lab on velocity versus time graphs next week as well. Okay, and then we'll start moving on to work and energy, but we still got quite a bit to go in this unit. I'm not at the point where I'm ready to put an exam date out there. Okay, it's probably going to be like the first week of June sometime. Okay, we're still a ways off. Okay, that's it for today, guys. Have a good weekend, but not too good.